This video is on Galilean and special relativity. Question 1. Define observer. An observer is a person who takes measurements from only one specific reference frame. Question 2. Define reference frame. A reference frame is a coordinate system which allows a specific value of time and position to a specific event. One reference frame is not better than another reference frame. Question 3. Define inertial reference frame. An inertial reference frame obeys Newton's first law of motion, the law of inertia. An inertial reference frame does not accelerate and does not experience a gravitational field. Question 4. Define event. An event is an instantaneous incident which occurs at a specific point in space. Question 5. Define simultaneous events. Two simultaneous events occur at the same time. Question 6. Define and state the equations for Galilean transformations. Galilean transformation equations are used to transfer coordinates from one reference frame to another. So x prime equals x minus vt, where v is the velocity of one frame of reference with respect to the other, or the relative velocity of two reference frames. T prime equals t means time measurements made by observers in both s and s prime are the same. And u prime equals u minus v. U is the velocity of a particle. So these equations should remind you of kinematics. And these equations have nothing to do with the derivatives. So do not think about derivatives when you see the prime. X prime does not mean the derivative of x. It means x in one reference frame. So the Galilean transformation equations do violate Einstein postulates, which you'll learn about later, hopefully. Question 7. Define Galilean relativity. Newton's laws of motion are the same in all inertial reference frames. The sum of velocities is v prime equals u plus v, where v is the velocity of an object moving in a frame of reference 1. U is the velocity of the frame of reference 1 with respect to the frame of reference 2, and v prime, which is not the derivative, is the velocity of the same object moving in a frame of reference 2. Question 8. State the two postulates of relativity. Number 1, the universality of time. The laws of physics are the same in all inertial frames of reference. Number 2, the universality of distance. Light travels in a vacuum with the same speed c in any direction in all reference frames. Question 9. A train is traveling horizontally to the right with a speed of 18 meters per second. A man on the train is walking to the right with a speed of 4 meters per second. Determine the velocity of the man by an observer at rest outside the train. So let the positive x direction be to the right. So you could see what was done here. Question 10. A train is traveling horizontally to the left with a speed of 32 meters per second. A man on the train is walking to the right with a speed of 4 meters per second. Determine the velocity of the man by an observer at rest outside the train. You could see what was done there. So the negative sign in the solution means the velocity is to the left. Question 11. Usain Bolt and Florence Griffith Joyner race each other. They both begin at the same time. Usain Bolt runs with a constant speed of 10.44 meters per second, while Florence Griffith Joyner runs with a constant speed of 9.53 meters per second. Part A, what is the distance between Usain Bolt and the starting line after 2 minutes? Okay. This is a kinematics equation. Part B, according to Florence Griffith Joyner, what is the distance to Usain Bolt after 2 minutes? So this is Usain Bolt's position after 2 minutes. This is Florence Griffith Joyner's position after 2 minutes. Part C, determine the speed of Usain Bolt as observed by Florence Griffith Joyner. Question 12. Wade Van Niekerk and Marita Couch race each other. They both begin at the same time. Wade Van Niekerk runs with a constant speed of 9.3 meters per second, while Marita Couch runs with a constant speed of 8.4 meters per second. What is the distance between Wade Van Niekerk and the starting line after 3 minutes? This is a kinematics equation. Part B, according to Marita Couch, what is the distance to Wade Van Niekerk after 3 minutes? So remember, this does not mean the derivative of x. This is the displacement of Wade after 3 minutes, and this is the displacement of Marita after 3 minutes. And this is the difference. Part C, determine the speed of Wade Van Niekerk as observed by Marita Couch. You just subtract the two. Question 13. What is the conclusion of the Michelson-Morley experiment? The speed of light in a vacuum is independent of the motion of Earth around the sun. Question 14. State the Lorentz transformation equations, define each variable. The Lorentz transformation equations give the space and time coordinates of events in one inertial reference frame and terms of those in another. So Lorentz transformation equations relate events in two systems. Okay. So these variables are not derivatives. X is one system, x prime is the other system. Y is one system, y prime is the other system. And t is one system, set of coordinates, t prime is the other set of coordinates. This is important. This is the relativistic velocity addition equation. We'll see some examples using this equation later, hopefully. Question 15. State and draw a Lorentz factor versus speed graph. So the Lorentz factor shows up frequently in relativity, and it's this equation. Gamma equals 1 divided by the square root of 1 minus v squared over c squared. And you can see if the speed of an object is 0, gamma is equal to 1. And as v gets bigger, this denominator gets smaller. So 1 divided by this small number becomes a bigger number. So if v goes to c, the speed of light, then gamma goes to infinity. So it looks like this. If the object is at rest, gamma is equal to 1. And you can see the horizontal axis is speed. And as the object speeds up, gamma goes to infinity, the value of gamma. So v goes to infinity, then gamma goes to infinity. Question 16. An event occurs at position 4 times 10 to the 3 meters and time 6 seconds. Where and when did the event occur according to a rocket travel horizontally in the positive direction at a speed of 0.4 c? The origins of both reference frames are 0 when both clocks read 0. So use the Lorentz transformation equation since an object is traveling near to the speed of light. So we're going to use these equations. So we have a value for gamma, we have a value for x prime, and we have a value for t prime. So do not round numbers early in the problem, because if you do, you're going to get numbers. You're going to get gamma that's like always equal to 1. And gamma is not always 1. Question 17. An event occurs at position -6 times 10 to the 3 meters and time 4 seconds. Where and when did the event occur according to a rocket traveling horizontally in the positive direction at a speed of 0.1 c? The origins of both reference frames are 0 when both clocks read 0. So use the Lorentz transformation equation since an object is traveling near to the speed of light. So gamma is equal to 1.00504. X prime we get to be this, and t prime we get to be this. Question 18. A rocket moves to the right past an IB school with a speed of 0.6 c. The IB school is located at the origin. Determine the time reading of the rocket if x equals 300 meters. The origins of both reference frames are 0 when both clocks read 0. So remember, t is equal to x over v. So we end up getting this value for t prime. Question 19. A rocket moves to the right past an IB school with a speed of 0.255 c. The IB school is located at the origin. Determine the time reading of the rocket if x equals 425 meters. The origins of both reference frames are 0 when both clocks read 0. So recall x equals vt. So now t equals x over v. And we could use that value to solve for t prime. Question 20. Describe time dilation and proper time interval. So imagine light being emitted and bouncing back. In the figures below, there is a light source or emitter and receiver on the top rectangle and a mirror on the bottom rectangle. So light is emitted from the top, it goes down, and then it goes back up. The observer who is at rest with respect to the events will observe that the light travels a shorter distance than an observer who is outside the rest frame. The events even occur at different positions or locations. So once again, this image on the left, imagine you emit a light, it goes down, and then it goes back up. You're at rest. Now imagine if you're moving to the right on a train. If someone is outside, the observer is going to see who's outside the train, the light go down, and then reflect back up. So the total distance traveled is going to be greater than if you're at rest. Okay. Time dilation is the lengthening of the time interval between two events for an observer in an inertial frame that is moving with respect to the rest frame of the events in which the events occur at the same location. So this is an equation we're going to see a lot. Delta t equals gamma delta t sub 0. Okay. We know what gamma is, it's the Lorentz factor, and v is the speed of the moving observer. So understand what it says on the bottom. Moving objects age slowly. Okay, in plain English. Delta t sub 0 is the proper time interval between two events, which is measured by an observer for whom two events occur at the same location. Delta t is a time interval between two events, which is measured by an observer for whom two events occur at different locations. Question 21. Describe length contraction and proper length. So L is equal to L sub 0 over gamma. L sub 0 is a proper length, which is a distance between 2 points measured by an observer who is at rest relative to both of the points. L sub 0 is the length of an object in its rest frame. Length contraction L is a decrease in the measured length of an object from its proper length when measured in a reference frame that is moving with respect to the object. L is the length of the object in the frame moving with velocity v. So in plain English, moving objects are thin. So imagine this is a sphere and it's moving to the right at a great speed. The vertical distance, it looks like 2 times the radius, but the horizontal distance is actually going to be thinner. So the vertical diameter will not change, but the horizontal diameter will decrease, as seen by an observer at rest outside the sphere. Question 22. Describe the twin paradox. There are two identical twins, Adam and Enoch. Adam stays on Earth. Enoch travels in space near the speed of light and returns to Earth after many years. Enoch ages much less than Adam. Enoch changes inertial reference frames when turning around. Question 23. A man at rest sees two objects traveling towards each other with a speed of 0.5 c. What is the speed of one object as seen by the other object? What would this value be using classical physics? So, using Galilean and special relativity, if two objects are going towards each other at 0.5 c, someone outside is going to see the two objects going towards each other at 0.8 c. Sorry, this is the speed of one object as seen by another object. Question 24. A man at rest sees two objects traveling towards each other with a speed of 0.9 c. What is the speed of one object as seen by the other object? So, using classical physics, we'll just add 0.9 plus 0.9, which gives us 1.8 c. But in fact, the speed of one object with respect to another has to be less than c. And that's what we get here, 0.994475. Question 25. Romeo is behind Juliet and is running towards her with a speed of 0.6 c as seen by a man at rest. Juliet is running away from Romeo with a speed of 0.4 c as seen by the same man as at rest. What is the speed of Romeo as observed by Juliet? So you could see what was done here. Question 26. Clyde is behind Terry and is running towards him with a speed of 0.355 c as seen by a man at rest. Terry is running away from Clyde with a speed of 0.255 c as seen by the same man at rest. What is the speed of Clyde as observed by Terry? What would this value be using classical physics? You could see what was done here. Question 27. A rocket is moving in a straight line with a constant speed v in space. It sends out a pulse of light ahead of it. How fast does the pulse of light move relative to an observer at rest on Earth? And the solution after you do it is c. So this is also the second postulate of special relativity. You could see our value was not greater than c. Question 28. A rocket at rest on Earth is measured to have a length of 45 meters and a diameter of 5.6 meters. The rocket is then launched toward Alpha Centauri, which is 4.30 light years from the Earth, at a speed of 2.20 times 10 to the 8th meters per second. What would be the length of this rocket as measured by an observer on the Earth? We just use this equation. Part B, what would be the length of the rocket as measured by an astronaut on board the rocket? Well, he's going to see the rocket as its length if it was at rest. Part C, what would be the diameter of the rocket as measured by an observer on Earth? So only the vertical length of the rocket will contract. So the diameter of the rocket as seen by an observer on Earth is still going to be 5.6 meters. Part D, what will be the distance to Alpha Centauri as measured by the astronaut on board the rocket? This is the solution. 2.92344 light years. Question 29. A rocket at rest on Earth is measured to have a length of 65.5 meters and a diameter of 7.65 meters. The rocket is then launched toward Betelgeuse, which is 427 light years from the Earth, at a speed of 1.25 times 10 to the 8th meters per second. Part A, what will be the length of this rocket as measured by an observer on the Earth? We're going to use this equation. Part B, what will be the length of the rocket as measured by an astronaut on board the rocket? It's going to be the same length. Part C, what will be the diameter of the rocket as measured by an observer on the Earth? So only the vertical length will contract, not the horizontal length. Part D, what will be the distance to Alpha Centauri as measured by the astronaut on board the rocket? It's going to be this. Question 30. The distance to the star Epsilon Indi as measured from the Earth frame of reference is 1.07 times 10 to the 17 meters. Part A, what is this distance in light years? So convert meters to light years. Now remember that light year has units of distance and not time. So this was the unit conversion here. Part B, what will be the distance in light years to Epsilon Indi as measured by an observer on a rocket heading towards the star at 85% of the speed of light? It's going to be this. Part C, how long in years will it take for this rocket to reach Epsilon Indi according to an observer on Earth? So let's use this equation, x equals vt, because this is an observer on Earth. This here is a unit conversion, and we get this many years. Question 31. The maximum distance to the planet Pluto as measured from the Earth frame of reference is approximately 7.50 times 10 to the 9 meters. Part A, what is this distance in light years? So what's here in this parentheses is a unit conversion. Remember that light year has units of distance and not time. Part B, what will be the maximum distance in light years to Pluto as measured by an observer on a rocket heading towards the star? Pluto is not a star, so we'll call it a fake planet at 80% the speed of light. This is the equation we use. Part C, how long in seconds will it take for this rocket to reach Pluto according to an observer on Earth? We're going to use the equation x equals vt. Question 32. A rocket is moving toward the star Delta Pavonis with a velocity of 2.4 times 10 to the 8th meters per second. The distance to Delta Pavonis as measured from the rest frame on Earth is measured to be 1.88 times 10 to the 17 meters. Part A. What will be the velocity of this rocket as a decimal fraction of the speed of light? 0.8. Part B. What is the distance to Delta Pavonis in light years? This is the unit conversion. Remember this. Part C. What will be the distance to Delta Pavonis as measured by an astronaut on board the rocket? Let's use this equation. Question 33. A rocket is moving towards the star Eta Cassiopeiae with a velocity of 2 times 10 to the 7 meters per second. The distance to Eta Cassiopeiae as measured from the rest frame on Earth is measured to be this. Part A. What will be the velocity of this rocket as a decimal fraction of the speed of light? It's this. Part B. What is the distance to Eta Cassiopeiae in light years? This is the unit conversion. Part C. What would be the distance to Eta Cassiopeiae as measured by an astronaut on board the rocket? It's this equation. Question 34. As measured from the Earth, the distance to tau CT is determined to be 11.8 light years. How fast in meters per second must a rocket be moving towards tau Ceti so that the distance to tau Ceti is reduced to 1.18 light years? So we're going to go from 11.8 light years to 1.18 light years. So we're going to have to be going pretty close to the speed of light to reach that. Question 35. As measured from the Earth, the distance to Ad Leonis is determined to be 16.1939 light years. How fast in meters per second must a rocket be moving toward Ad Leonis so that the distance to Ad Leonis is reduced to 12 light years? So we're going to go from 16.1939 light years to 12. So we're still going to be going pretty close to the speed of light. Question 36. How fast must a rocket be moving in order for its length to be reduced to 50% of its rest length? Once again, pretty close to the speed of light. Question 37. How much must a rocket be moving in order for its length to be reduced to 1% of its rest length? Really close to the speed of light. Question 38. According to an observer on the Earth, the time it should take to reach a certain star is determined to be 7.5 years. How long will it take to reach the star according to an observer on board a rocket moving towards the star with a velocity of 0.985 c? A lot less. Question 39. According to an observer on the Earth, the time it should take to reach a certain star is determined to be 22 years. How long will it take to reach the star according to an observer on board a rocket moving towards the star with a velocity of 0.8 c? It's 13.2 years. Question 40. The distance to Barnard's star is measured to be 6 light years by an observer at rest on the Earth. Part A. Assuming that a rocket is moving towards the star at 0.98 c, how long in years will it take for this rocket to reach Barnard's star according to an observer on the Earth? So this is a kinematics equation. Part B, how long in years will it take to reach the star according to an observer on board the rocket? About 1.21835 years. Part C, what will be the distance in light years to Barnard's star according to an observer on board the rocket? Now it says distance here. So now we're going to have to use this equation. It's about 1.19398 light years. Question 30. Assuming that the astronaut was 21 years old when she left the Earth in 1988, and what year will the astronaut arrive at Barnard's star according to an observer on Earth? So it's 1988 plus 6.12245 years. Part E, how old will the astronaut be when she arrives at Barnard's star according to an observer on board the rocket? If she was 21, now she'd be 22. Part F, suppose that the astronaut has a normal heart rate of 65 beats per minute when measured while at rest on Earth. What would be the astronaut's heart rate as monitored by an observer on board the rocket with the astronaut? It's still going to be the same. Part G, what would the astronaut's heart rate be while on the rocket moving towards Barnard's star as monitored by an observer on the Earth? It's going to go for 65 beats per minute to about 13 beats per minute. Question 41. The distance to Groombridge 34A is measured to be 11.6191 light years by an observer at rest on the Earth. Part A, assuming that a rocket is moving towards the star at 0.822 C, how long in years will it take for this rocket to reach Groombridge 34A according to an observer on Earth? So just use this Suvat's kinematics equation. Part B, how long in years will it take to reach the star according to an observer on board the rocket? We're going to use this equation. Part C, what will be the distance in light years to Groombridge 34A according to an observer on board the rocket? We're going to use this equation. Part D, assuming that the astronaut was 32 years old when she left the Earth in 1988, and what year will the astronaut arrive at Groombridge 34A according to an observer on Earth? So what's 1988 plus 14 years? Part E, how old will the astronaut be when she arrives at Groombridge 34A according to an observer on board the rocket? It's going to be 32 plus that. Part F, suppose that the astronaut has a heart rate of 62 beats per minute when measured while at rest on the Earth. What will be the astronaut's heart rate as monitored by an observer on board the rocket with the astronaut? It's going to be the same. Part G, what will the astronaut's heart rate be while on the rocket moving toward Groombridge 34A as monitored by an observer on the Earth? We're going to use this equation. It's going to be less than 62. Question 42. Two astronauts play a game of chess on a rocket moving with a velocity of 0.999 c away from the Earth. According to the astronauts, the game takes 2.5 hours. How long in hours does the game take according to an observer at rest on Earth? It takes about 56 hours to finish. That's a long chess game. Question 43. Two astronauts are taking a very boring online IBHL physics class on a rocket moving with a velocity of 0.9 c away from the Earth. According to the astronauts, the boring online IBHL physics class takes 90 minutes. How long in minutes does the boring online IBHL physics class take according to an observer at rest on Earth? That's how you do it. Question 44. A rocket is moving toward Epsilon Eridani, which is 11.3 light years away as measured by an observer at rest on the Earth, at 0.998 C. When the astronaut leaves the Earth in 1991, he has just had his 22nd birthday and his young daughter has just turned 1 year old. The rocket travels to the star, remains there for 6 months, and then finally returns to the Earth at the same speed. A. In what year will the rocket return to the Earth? So, this is the time to reach Epsilon Eridani. Let's multiply that by 2, coming and going, and add 0.5 because we were there for 6 months, or the astronaut, and add 1991 to it. So they'll return in maybe sometime in 2015, I guess, or 2014. Part B, how many years will the journey take according to the astronaut on board the rocket? Step 1, find the light years. Step 2, find the time. Step 3, add up the time. It's about less than 2 years. Part C, how old will the astronaut be when he returns to the Earth? About 24 years. Part D, how old will his daughter be when he returns to the Earth? Around 24 years. Question 45. A rocket is moving toward Luyten star, which is 12.3485 light years away as measured by an observer at rest on the Earth, at 0.855 C. When the astronaut leaves the Earth in 1992, he has just had his 32nd birthday and his young son has just turned 2 years old. The rocket travels to the star, remains there for 3 years, and finally returns to the Earth at the same speed. A. In what year will the rocket return to the Earth? So this is the time. We're going to multiply it by 2 because we're going to be coming and going. The rocket remained there for 3 years. Part B, how many years will the journey take according to the astronaut on board the rocket? So first solve for L. This is the light year. Then solve for the time. We're going to multiply it by 2 because we're coming and going. We're going to add 3 years for the stay. Part C, how old will the astronaut be when he returns to the Earth? This part was solved here. Part D, how old will the sun be when he returns to the Earth? Question 46. Two twins are 22 years old when one of them sets out on a journey through space with a constant speed. The twin on the spaceship measures time with an accurate watch. When he returns to Earth, he claims to be 28 years old, while the twin left on Earth is 40 years old. What was the speed of the spaceship? So we want to solve for V. And we get this solution here. Question 47. Two twins are 34 years old when one of them sets out on a journey through space with a constant speed. The twin in the spaceship measures time with an accurate watch. When he returns to Earth, he claims to be 38 years old, while the twin left on Earth is 44 years old. What is the speed of the spaceship? Well, it took 10 years according to someone on Earth, for the rocket to come back, the spaceship. And we just solved for V. Question 48. A neutron outside the confines of the nucleus of an atom is unstable and has a life expectancy of 6 minutes. Suppose that a fast-moving alpha particle collides with a block of beryllium and knocks a neutron out of the nucleus with a speed of 8.15 times 10 to the 7 meters per second. What would be the expected lifetime of this neutron as measured by an observer in the rest frame? It's about 6.23447 minutes. Question 49. A neutron outside the confines of the nucleus of an atom is unstable and has a life expectancy of 6 minutes. Suppose that a fast-moving alpha particle collides with a block of beryllium and knocks a neutron out of the nucleus at a speed of 7.25 times 10 to the 7 meters per second. What would be the expected lifetime of this neutron as measured by an observer in the rest frame? It's the same procedure, right? Question 50. Describe the equation of the space-time interval delta S. Describe proper time interval and proper length in terms of the space-time interval delta S. So, remember we have two frames of reference here. The space-time interval delta S is given by this equation. Okay. All three sides have the units of length. The left side, the middle side, and the right side. Remember, c is the speed of light. The equation tells us that two different observers may measure different time intervals and different distances between two events, but both observers will agree on the space-time interval between the two events. So, two different observers may measure different delta t's and different delta x's, but their delta s squared will be the same. So delta t sub 0 is the proper time interval between two events, which is measured by an observer for whom two events occur at the same location. And delta t is the same time interval, is the time interval between two events, which is measured by an observer for whom two events occur at different locations. You've seen this before. L sub 0 is a proper length, which is the distance between 2 points measured by an observer who is at rest relative to both of the points. L sub 0 is the length of an object in its rest frame. So, if we have a time-like interval in which a physical event, like a clapping of a hand, is separated in time but not in space, we have this equation. A space-like interval, a physical event, is separated in space, but not in time. We have this equation. A light-like interval is a physical event is separated by the speed of light. Question 51, describe the relativity of simultaneity. So check this question out. You have observer A on a train and observer B outside the train. Observer A flashes light. And as the train moves to the right, the light that hits the back side of the train reaches the back quicker than the light reaches the front of the train. But the light that reaches the front of the train is going to go back to observer A quicker than the light from the back of the train meeting observer A. And observer B Yeah, and while observer A is going to see both light hit the front and back of the train at the same time and reach him at the same time. So imagine observer A is sitting in the middle of a train moving at constant speed to the right. Two flashes of light are simultaneously emitted from observer A to the front of the train and the back of the train when observer A and observer B have the same position coordinate x equals 0 meters. The two flashes of light will reflect off the ends of the train and reach observer A. So, like I said, if you're observer A, you see the light reach the back and the front of the train at the same time, and it reflects and it reaches observer A at the same time again. Observer A, who is sitting in the middle of the train and is at rest, sees both flashes of light reach the back of the train and the front of the train at the same time. They are both reflected at the same time and reach him at the same time. Let's talk about observer B. Since this train is moving to the right, there's going to be less distance for this light to reach the back of the train than the front of the train. According to observer B, because the train is moving to the right, the flash of light which is emitted to the back of the train will reach the back of the train before the flash of light which is moving to the front of the train. Observer B believes that the two flashes of light are not traveling the same distance to the ends of the train. After the light gets reflected, it seems that the light from the back of the train travels a longer distance than the light reflected from the front of the train. Observer B sees both flashes of light reach observer A at the same time. So conclusion, time intervals have different values when measured in different inertial frames. Question 52, draw and label the axis of a space-time diagram. So just write plus ct on the vertical, plus x on the horizontal. Notice they both have the same units, which is distance. Okay. Both the horizontal and vertical axis are scaled equally. So for example, if 1 centimeter on the horizontal is 1 light year, then 1 centimeter on the vertical is also 1 light year. Question 53, draw a space-time graph where two events occur at the same time and another space-time graph where two events occur at the same location. So if they occur at the same time, you have horizontal points. So these are called simultaneous events. Two events which occur at the same location but different times are called equilocal events. You can see this is a vertical line. So this image on the left, as you move up, the CT is the same. And this image on the right, as you move up, the CT is different. And this image on the left, as you move to the right, the X's are different. And this image on the right, as you move to the right, the X's are the same. Question 54, use a pencil and ruler, define the world line, draw a world line in a space-time graph of an object at rest, the second object moving with a velocity of 0.4 c, and a third object moving with a velocity of 0.8 c. So world line is a path through space-time of a particle traveling at a constant velocity. The angle of the world line is taken from the vertical axis, not the horizontal axis. So a red line is an object at rest. The green line is an object traveling at 0.4 c, so its slope is less. And finally, the brown line is an object traveling at 0.8 c, so that slope is less, decreases. So the world line does not have to pass through the origin. Question 55. Describe the relationship between the angle between the world line of a moving particle and the time axis on a space-time diagram. So, if the object is at rest, then theta is 0 degrees from the vertical. Okay, so it's just a vertical line, just like this red line here. So if the object is traveling faster and faster, then theta from the vertical increases. So if an object is traveling at the speed of light, then theta is going to be 45 degrees from the vertical. So the maximum angle of a world line in a space-time graph is 45 degrees. 56. Use a pencil and ruler and add another reference frame to a space-time diagram. On the space-time diagram, label an event and describe how that event takes place at two different times in both reference frames. So I just added another reference frame to a space-time diagram. So we have an event P. The length of xp, this black vertical line, is not equal to x prime p, this almost vertical blue line. So event P takes place at different locations. And the length of CTP, which is this horizontal black line, is not equal to CT prime P. So event P takes place at different times. Question 57. Use a pencil and ruler, draw a diagram with two reference frames. Label 4 stationary events in an x prime CT prime graph. Draw a second diagram with two reference frames. Label 4 events which occur at the same time in a x prime CT prime graph. Remember, once again, this prime does not mean derivative. So these are stationary events at the same location. These green dots. Because if you go up this purple line, you'll notice that it's at the same x prime, just different CT prime. Now this image on the bottom is at the same time, because as you go up the x prime graph, you're going to reach these 4 green dots at the same CT line. Question 58. Below is a space-time diagram with 2 reference frames and 5 events. Determine the order of events according to the x CT graph and the x prime CT prime graph. So let's just make a horizontal line parallel to x. When we go up, we're going to reach we're going to reach event 1 first, then 2 and 5 at the same time, and then 3 and then 4. Okay? So take a line parallel to the plus x graph and move up. Now let's look at the x prime CT prime graph. Let's make a line horizontal to this blue x prime axis and move up. So 1 and 2 occur at the same time, and then 5, and then 3, 4. So take a line parallel to the x prime graph and move up. So you notice for 2 different observers, these events happen at 2 different times. Interesting. Question 59. Draw and describe a graph of delta S squared equals -1. So we need to be a little familiar with the equation of a hyperbola and drawing hyperbolas. So consider this equation. Let x ct be 1 comma 0. So now we have delta s squared equals minus 1. So now we could graph the hyperbola delta s squared equals minus 1. So we are scaling the spatial axis of the moving observer. So the space axis of objects moving at different speeds are scaled differently. The faster an object moves, the longer a unit of length in the system becomes. So you could see green is moving at a fast speed, blue is moving even faster, purple is moving super fast. And you could see the length is longer for purple than blue and longer for blue than green. So in conclusion, the scaling is different for a moving system than a resting one. Okay. So draw and describe a graph of delta s squared equals plus 1. So let x comma ct equals 0 comma 1. So now we graph the hyperbola delta s squared equals 1. Okay. So now we're scaling the time axis, this black curve on the right side. The time axis of objects moving at different speeds are scaled differently. The faster an object moves, the longer a unit of time in the system becomes. So remember, green is moving slow, blue is moving faster than the green, and purple is moving faster than the blue. So you can see the purple has a longer length on the x-axis than blue, and blue has a longer length on the x-axis than the green. Question 61. 3 observers, left, middle, and right, are separated a distance a from each other on a parallel line. They all travel from rest to a speed of 0.4 c to the right and remain a distance a from each other. The observer in the middle, M, sends out a light pulse in all directions. The light gets reflected from observer L and observer R and returns to M. Does observer M receive the light pulse from observer L or observer R first? So the world lines, these slopes should all be parallel to each other. My Microsoft Paint skills are terrible, I apologize. So observer M receives light from both observer L and R at the same time. So remember, all 3 of these observers are going to the right at the same time. They're all out 0.4 c, and they're both, L and M are separated by a distance a, and M and R are separated by a distance a. You could see the light to reach M to L is going to reach M to L quicker than middle to right, because this brown line is longer. But the light to reach right to middle is going to be shorter in time than the light to reach left to middle, since they're all moving to the right. So this brown box should be a perfect rectangle, and I apologize that it's not. So the brown box should be a perfect rectangle. Sorry about that. So L means left, M means middle, R means right. Question 62. Describe a muon decay. Muons are formed in the upper atmosphere from collisions between cosmic ray particles and nuclei. The muons travel towards the surface of the Earth with varying speeds. The proper time interval, 2 events which is measured by an observer for whom 2 events occur at the same location, of the half-life of the muon is approximately 1.52 microseconds. According to classical physics, very few muons should reach the surface of the Earth. Faster moving muons will reach the Earth due to time dilation since they live longer as measured by an observer on Earth. Faster moving muons will also travel a shorter distance to Earth as measured by the muons than an observer on Earth. The observer on Earth will measure the proper length L sub 0. So one observer will witness time dilation, the observer on Earth, and another observer will witness length contraction, the muon. Neither observer will observe both. So this is what we have here. Look at this brown vertical line and this black vertical line. The black vertical line on the left-hand side tells us the time it takes for a muon to reach the ground according to an observer on Earth. So according to an observer on Earth, it's going to take a long time, longer than that of the muon. The vertical brown line on the left-hand side tells us the time it takes for a muon to reach the ground according to the muon. So the muon's going to observe a shorter time to reach the Earth. Take a look at this brown and black horizontal line. The horizontal brown line on the bottom tells us the length it takes for a muon to reach the ground according to an observer on Earth. And the horizontal black line, L prime on the bottom, tells us the length it takes for a muon to reach the ground according to the muon. So the muon's going to think that it's going to travel less distance.